Hi, good morning. So today, as I mentioned from the 3-minute long test video, in this lecture, we're going to start talking about biomechanics of work. So biomechanics is an important topic for physical ergonomics. In the first half of the semester, we talked a lot about the cognitive side of human factors, including vision and illumination, symbol design, display design, text design. That has a lot to do with human factors. So even though there's a lot of similarities between the terms human factors and ergonomics, there are slight differences and divisions. So I would say that text and display control design, a lot of it belong to human factors. How your body moves and works is more physical ergonomics. So today and in the future few lectures, we're going to talk more about physical ergonomics. So starting off, to talk about biomechanics, there's no escaping of talking about the musculoskeletal system. So essentially the musculoskeletal system is how your skeletal and muscles work together as a system. So as the picture shows on the right, it's a very intricate system with a lot of components, and they all synchronize together and work together. So it's actually very, very amazing how every single part is not imitable and they all work together as a whole. So the musculoskeletal system is composed of, for the most part, bones, muscles, connective tissues. So the connective tissues can be broken down into 4 parts: ligaments, tendons, fascia, and cartilage. If those terms sound foreign to you, you shouldn't be worried about it at this point. We're going to hopefully break it down and talk about it in enough detail for you to understand the musculoskeletal system so that you can apply it in terms of physical ergonomics and biomechanics. So let's talk about, before we dive in greater detail in anatomy and physics, let's talk about why musculoskeletal disorder prevention and intervention are important. If you remember from the first half of the semester, I sometimes would talk about where my research interests are, and MSD prevention and intervention are a large part of my interest. So I'm actually very excited to be talking about this. It's a shame that I can't really, the circumstances are not permitting me to talk about these topics in person, but I'm so excited to share these knowledge through the screen. So we had a dedicated few lectures talking about anthropometry. In that, I hope you remember that we discussed the importance of ensuring the fit between physical dimensions of products and workplaces and the body dimensions of the user. And I also hope that you remember the picture from the right when I talked about how a system may require the users to use their bodies to control certain things using certain physical controls, as shown in the top right picture. It's intended to be designed for a person with normal proportions. However, if you do the analysis using anthropometry, you'll be able to find out that the ideal person to use these specific set of controls is terribly disproportional. And I did mention in our anthropometry class that for a normally proportioned person to do this type of work that's designed disproportionately, in order to get it done, the person may have to adopt some very awkward postures. Using these awkward postures for a prolonged period of time, it's very likely that this person, over repetition and repeatedly exerted force, he or she is going to develop some sort of musculoskeletal disorders or injuries. So that is no good news for any employers or employees. That is part of the reason why we wanted to study MSD's prevention and intervention. And it's important to note that awkward postures are not the only factor that can cause physical stress to the body. There's a series of risk factors. 4 of them are confirmed, including confirmed by literature, including force, repetition, awkward posture, and vibration. So vibration, you can think of examples as jackhammering. It happens a lot in construction sites among construction workers. You can also think about, I talked about truckers during one of the lectures, and then the truckers, they drive all day in a relatively large vehicle, and the vehicle has certain type of vibration. So that vibration is actually harmful to the human body if it's experienced through a long term. So we can talk about the MSDs that are specifically associated with these risk factors in the latter part of this lecture. So for force, it's pretty intuitive. So the load during either cyclic loading or non-cyclic loading is a determining factor of MSDs. The repeated exertion of the force is also a factor. It's in the recent years that's found out that force and repetition actually have an interactive effect on musculoskeletal disorder development. So I recommend you read this article that's assigned on the right, right here. So click on it. It's a scientific journal, so treat it as a reading assignment, and I won't talk too much about it in this lecture. Awkward posture, we already talked about. Vibration, we already talked about. So let's move on. So here I'll use some stats to discuss why MSD prevention and intervention are important as a continuation of the previous 2 slides. So I'm sure there's new data that's being published right now, but as far as what I can find is in 2001, 4.9 million non-fatal occupational injuries were reported. So those are 4.9 million non-fatal occupational injuries that are associated with musculoskeletal disorders. As a whole, musculoskeletal disorders account for about 1/3 of all non-fatal workplace injuries. The direct and indirect costs of MSD sum up to billions of dollars annually. So 1 in 20 people will suffer debilitating back pain sometimes in their lives. Some stats actually report, it's a different article that's reporting differently than the stat of $2.6 billion. Some literature actually reported that low back pain related worker compensation payments and indirect costs total about $27 to $56 billion. So the total cost of low back pain to the US total about $33 to $36 billion. So there must be some inaccuracies about these reports, but just remember that they cost a lot. They not only cost the employees a lot in terms of their living quality, but they also, from an employer's perspective, if you one day work for an organization, either large or small, you're going to have to think for the sake of the employer. So from their perspective, MSDs are not good, not only in terms of hurting the workers, making their life quality decrease, affecting worker satisfaction and productivity, but also that it's actually costing the actual dollars from the employers to pay for workers' compensation. So that's a big deal. So now that we understand learning the development of musculoskeletal disorders, as well as how to prevent and intervent musculoskeletal disorders are important, we want to talk about how we can help, how we can improve the process of intervening and preventing MSDs. So there's a whole subject that's called biomechanics. That's learning about the motion of the human body, of the musculoskeletal system. And to study musculoskeletal disorders, prevention, intervention at work, that's as is work related. The work related musculoskeletal disorders actually is usually abbreviated as WMSDs. To study WMSDs, occupational biomechanics is directly relevant to that. So occupational biomechanics is a science concerned with the mechanical behavior of the musculoskeletal system and component tissues when physical work is performed. So it seeks to provide an understanding of the physics of manual activities in industry. This is a direct quote from a giant from this occupational biomechanics field, Chaffin. So if you get a chance, you can check it out. It's from Chaffin, Anderson, Martin, their publication from 2006. I can post the journal article if you'd like, either in this slide when I post it on my courses, or I can do it in the announcements. But treat it as a reading assignment. It's, as I said, Chaffin, as well as Anderson and Martin, they're all really big buffs in the field. And Chaffin actually created a biomechanics model that I will be talking about and emphasizing in the latter part of the lecture. So hopefully you'll learn more about this through this lecture. So biomechanics is a interdisciplinary science that integrates knowledge and techniques from diverse physical, biological, and engineering disciplines. So this is really in line with our introductory lecture on ergonomics and human factors. Just overall, it's interdisciplinary, and specifically for biomechanics, it has to do with physics, biology, and engineering. So let's look at the bone structure of the human body. That's the skeletal part of the human body. There are 206 bones in the human body. The bones form rigid structure of the human body, and they play major supportive and protective roles in the body. You don't have to remember all of the bones that's shown in the right, labeling all of the bone, not all of, but the major bones in the human body. But I always am fascinated by the structure of the human body, and I think memorizing and learning about what is what and what is where is really fun. So I think it's a good thing to learn, and it's part of you. So I always think that it's fascinating to learn what's going on, like in me and everybody else. So if you're interested, feel free to look it up and look up more information online. There's a ton of good information online, and the book that I've been referencing to for the pictures that I use in this lecture is from this Atlas to Anatomy. It is not my book, but it's a renowned book. I have a different book that unfortunately I left in the office, and I couldn't return. I didn't want to return to the office to retrieve it, so I borrowed it from my husband. That's his book, but it serves a really good purpose. All of the drawing, almost all of the intricate drawings that I'm showing in this lecture, I took scan from this atlas. It's really amazing how nicely reflected the human body can be through really nice art and drawing. So let's look at some of the bones by its function. So some of the bones protect the internal organs. So for example, in this picture that I'm showing right here, it's not from the book, but I try to show a simplified picture with clearly defined regions in colors to show the main bones of the skull. So the skull covers and protects the brain. So that serves one big part of function of the bones in general. And the other example of the protective functions of the bones is exemplified by the rib cage. So the rib cage, a lot of us know that inside of the rib cage, it protects the lungs and the heart and the major vital organs of our body. So without it, it can easily be hurt or be injured. So the rib cage really shields it from a lot of injuries. So let me actually, yeah, this is the benefit of conducting the course online, so I can correct as I go. Hopefully there won't be many errors. So the other function of a lot of bones is to support the body movements and activities. So it not only protects, but also supports movements. So a good example is in your legs, the big bone, thigh bone in your legs is called femur. It's connected through a patella, that's your knee bone, kneecap. And then tibia is a large bone in your shin. You can call it the shin bone. And fibula is a supportive bone, a smaller bone. So the femur and tibia really support make the structure of your leg as you move around. They support your activity and movement as you run and skip. So, as I mentioned before, there are four main types of connective tissues, and I will talk about them one by one because they're very important in terms of understanding human movement and how they move and how they can potentially get injured. So tendon is the first type of connective tissue that I like to talk about. Tendons are dense fibrous connective tissues that attach muscles to bones and transmit the forces exerted by the muscle to the attached bones. So the example that I'm giving you right here is a major tendon in our body. On the right, you can see a pair of Achilles tendons, or they're really big tendons. They connect the heel to the gastroc. The gastrocnemius muscles, short for gastrocs. The soleus is an inner muscle, and we won't really talk about it right here, but the Achilles tendon, that's an example of tendon. As you can see that the muscles are marked red because they're full of capillary and vessels and blood flow, but tendons not so. It's a different fibrous structure, and it's actually, if you see it in cadaver, it's actually much more white than any of the muscles. So second type of connective tissue is ligaments. It is also a dense fibrous tissue, but different than tendons, which serves the purpose of connecting muscles to bones. Ligament actually connects bones to bones. So I give you a good example in the body, a major joint in the body. That's our knee, and this is a representation of our knee. Patella, as I mentioned earlier, is the kneecap, and as you flex and extend your knee, actually the femur and tibia glide and slide around the patella, so around your kneecap. And if you're a big fan of sports, maybe football, sometimes you'll hear unfortunate events where during tackles or some severe or acute movements, the football players will sometimes injure or tear their ACL. You hear the sports announcer will say, oh, unfortunately, so-and-so tore their ACL, or PCL or hurt their meniscus. This is inside of their knee, and you can see the structure of it. And this is the anterior cruciate ligament, and that's short for ACL. Posterior cruciate ligament is the PCL. So we, actually in the midterm, we gave you a question of the different planes of the body, right? So, oh, that's my fault. So anterior means more in front. So the anterior side meaning the front side. If you're looking in front, then the front side of your body, towards the front side of your body. Posterior cruciate ligament, posterior meaning more towards the back. So this is exactly what it means. So the anterior and posterior cruciate ligaments form across, just about like this. So anterior is in front and posterior is more in the back. So remember the ACL and PCL. They get injured a lot in athletes and non-athletes. So there are other ligaments, you know, connecting the femur to the tibia, medial and lateral. Remember, we talked about the planes of the body. So medial is more towards the center of your body, lateral more towards the side. So if you have any questions, to just go back to our lecture where we talked about, you know, we tested your cranial and caudal, you know, lateral, medial, anterior, posterior. So learn about that. It may show up again during the final, because this is very important. When you refer to different body parts, this is a golden standard you have to follow. You can't really say, oh, in front of the body, back of the body, whose body, right? So it's good to have some universal standardized terms, and it's important for you to learn that and put it in your working memory. So we talked about ligaments, and then this is a picture from the Atlas book that I just showed you. Cartilage is a translucent elastic tissue that can be found on some articular bony surfaces and some organs, such as the nose and the ear. So your nose is kind of semi-rigid. The tip of your nose has some cartilage, so it can be wiggly. Here I showed you a picture of, again, the knee, but it's a different view of the knee. So as if in this picture, you're looking at the knee from, as if you're looking at another person's knee. This is as if you're looking from above to below. So you're looking at this plane right here in this picture. So the cartilage, this half moon-shaped tissue is called the meniscus. So the plural is menisci. So the menisci in your knee is made up of cartilage. It is a type of connective tissue. And I think it's there are definitely other cartilages in your body, as I said, in your ear and nose, but I think this is most relevant to our work in terms of biomechanics, and it covers a relatively large, is a pretty prominent cartilage. So I think it's a good example to show. Here's a better picture of it, a larger picture in case you wanted to see all the labels. And there's not only cartilage, a menisci that's on the outerior, there's also menisci that's on the interior. So right here. So the medial meniscus and lateral meniscus, they're more on the inside, and then the other menisci is more on the outside. The fourth type of tissue is important, but not as rigid. It's called fascia. Fascia covers body structures and separates them from each other. So the example that I'm giving you here is in the gluteal region, more on your, like around your hip. So as you can see, I give you different layers of it. So, oh, I don't know why I did that again, sorry. So this is a gluteal fascia. As you can see, there are some small blood vessels on it, but it covers covers the large muscles on, you know, this is the gluteal region hosts some really large muscles. For example, gluteus medius and gluteus maximus are the muscles that's wrapped and protected underneath this large piece of fascia. So as if you're peeling away the fascia, you should be able to see the large muscles that I just talked about underneath. So now let's move on to talk about joints. What's defined as joints? There are two or more bones that are linked together with each other at joints. Joints can be classified to a few types through a couple of different ways. So the first way of classifying joints is just by its type. So it's either synovial, fibrous, or cartilaginous joints. So we'll talk about this way of classification first. So a synovial joint actually is the most prominent type of joints. It's seen a lot in human bodies. So there's no tissue existing between the highly lubricated joint face surfaces. The example that I gave you right here is the shoulder joint. The shoulder joint is actually the most mobile joint in your body altogether. It's the #1 most mobile joint. It can move 360 degrees. It's also called technically the glenohumeral joint. So as you can see here, this structure, structure right here is the joint, and then this kind of whitish tissue right here is highly lubricated. Between this surface and this surface, highly lubricated, that facilitates the free mobility and movement within the joint. #2 type of joint is the fibrous joint. So as you can see here, there are a lot of sutures in the adult skull bone. There are many sutures. So for example, the coronal suture, as well as, let's see, squamous suture. A lot of these sutures were connected with cartilage when we're babies. So if you hear that the babies have soft spots on the top of their head, and this is their fontanelle. Their fontanelle in adult humans, it becomes rigid bone. So if you touch your forehead, if you're an adult, it's probably just one piece of bone that's rigid. But in babies, sometimes you'll see their head pulsing, and that's because their joints, the sutures, have not been formed yet, and their head is flexible so that they can, their head can change slightly in shape when they're during the birth process through the birth canal, and then between years 0 to 2, they slowly but surely start to form a rigid structure, and the sutures start to close. So they became fibrous joints. These joints, they're rigid, they don't move, they don't facilitate movement, they're just there, symbolizing, adult growth, and they're done forming the skull. And they protect the contents in there, which is the brain. Let's see, okay, yeah. The third type of joint is the cartilaginous joint. These are bridging joints. So the example that I gave you right here, remember I drew on the board when we were still able to meet in class, when I was introducing the lumbar lordosis and kyphosis curves. If you don't remember, look it up. It may show up in the final. So when I was talking about the curve of the spine, I was introducing the intervertebral discs and how the intervertebral discs can start to deteriorate and herniate. This is the disc. This is the a cross section of the disc, and how the disc connects with the intervertebral bone is that it's connected to a hyaline cartilage end plate, and this whitish cartilage is called hyaline cartilage, and it's also a cartilaginous joint. They connect with the discs, and then it's kind of like a sandwich. So this bone, actually, there's another piece of intervertebral bone up here, and then they sandwich the disc and make such a joint. So that's one type of classification of joints. And the joint types can also be classified in another way, by movement types. So I'll show some repetitive pictures because I feel like this will help you make a connection between, or also help you distinguish the difference between the two types of classification. It's important to understand how the joints can be classified differently because obviously there are different reasoning behind the different types of classifications. One is by its material type, the other is by its movement or function type. So now let's talk about classification by movement types. Number one type is no mobility joints. So we just talked about sutures. Sutures are not meant to be moving around. So they are meant to be rigid and protective of the brain, the contents that are inside. Number two type is the hinge joints. So the hinge joints, we have a lot of them in the hands and the feet. So your fingers can only move 180 degrees. It cannot move this way. It can only move this way. So it permits motion in only one plane. And a good example is the finger joint, and you can also look in your toes, and they are also hinge joints. The third type of joints by movement is the pivot joints. A good example, I showed you again this picture, but let's look down on the wrist. The wrist allows 2 degrees of freedom of movement. So it can do this, it can also do this. So it's 2 degrees of freedom. It's different than just one plane of movement like this, like your fingers. So I gave you a YouTube video. I think it probably won't do too much good if I click on it and we just all watch online. We're online anyway, so I'll prompt you to watch it in your own time. It is a valuable video to watch. I think it's well made, so I highly recommend you watch it in your own time. The fourth type of joint is the ball and socket joint. I've already showed you the glenohumeral joint in the shoulder right here. So it has 3 degrees of freedom, and it can move along the x-axis, y-axis, and z-axis, so like 360 degrees, all you want. It also applies to your hip joints. So hip and shoulder joints are really flexible. They're ball and socket, literally. This is the ball, and that is the socket. So it kind of works in this fashion, very, very fluid. And remember, I talked about the classification before. It's a lubricated joint, and this type of material is hyaline cartilage, right? It's highly lubricated, facilitates very mobile movements. Then we'll talk about Wolff's Law and bones change because of different reasons. So bone can change in structure, size, and shape over time. It's kind of amazing to think about because a lot of the bones, it seems all very rigid and firm, just from our experiences, but they do change over time, over your lifespan. I talked about how the skull bones change from a baby to adult. They change in size. Obviously, we all grow taller and bigger as we age, from infant to child to adolescent to adult. And then from going from adult to senior adult, our bones also change in its components and structure. So a lot of times the change actually is a result of mechanical loads placed on them. So this is an important law. in bone growth and changes. So Wolff's Law says that bones are deposited when needed and are resorbed when they're not needed. So this should be a good motivation for everybody to go out. We're in social isolation, but it shouldn't prevent you from, go out alone to a less crowded place and exercise, right? Or you can exercise on your own apartment if you want to. It's basically saying that if you don't use it, you are going to lose it. So if you don't exercise or deposit certain forces into certain joints or bones, your body somehow gets the signal that it's not going to get needed to either exert certain forces or to take certain forces, then the bones are actually going to be less likely to be deposited on that site. If you continue to exercise it, not over exercising, but keeping it used and exercised, then your body will send the signal that, oh, this joint and bone is being used on a regular basis, and let me deposit more bones on it. Basically, that's layman's term for Wolff's Law. Although it's also stated that precise relationships between bone changes and mechanical loads remain unknown. What does that mean? That means that it's not really known quantitatively how much load either you lift or you exert can lead to however much bone deposit or bone changes. Or in other words, how many weeks, months, or years that you do not exercise will lead to osteoporosis, meaning that the loss, the bone loss or bone density going down. You can, as you can see, probably notice in some of the older adults, their spine started to curve like this. They started to go like this. That's osteoporosis. They lose their bone structures, become less dense and less supportive, and it actually eventually changes in shape. So even though the precise relationships are not known, study has also already shown that regular exercise and good nutrition can effectively prevent osteoporosis progression. So, and also, of course, during a long process of loading, unloading, the bones will grow and deposit. But in a sudden event, bones can also fracture when they're exposed to a large amount of loading or excessive loading or repetitive loading. So it has to do with load, number of repetitions, and frequency of the load to decide sometimes whether the load is too excessive or too injurious. Okay, so we've just talked about the bones. Let me see how much longer we have. Okay, yeah. We actually have a lot more to talk about in terms of muscles. So I will stop right here at the end of bones, and I'll try to label this as, I'll try to label it nicely so you'll be able to tell what this is, what this chunk section is about. And then in the next one, I'll continue to talk about muscles. All right, I'll stop right here.